In this lesson, we're going to talk about how it is that magnets themselves rotate in an external magnetic field. For example, if you take a compass needle, it turns out the compass needle itself is magnetized, and that magnetic field wants to align with the external magnetic field. Now, in our next chapter, we're going to learn how it is that the currents themselves, the moving charges themselves, make their own B field. So the coil, the current that we were just talking about, that blue current flowing through a coil, and that coil rotates in the presence of the external magnetic field that we have over here. So that current, that blue current I, is going to actually make its own B field, which I'm going to leave in blue. So it's going to make a blue B field, its own B field. And we're going to learn again more about that in our next chapter. But we now understand how it is that these coils, right, these N coils, 1, 2, 3, 4, 5, 6, 7, 8, 9 coils, rotate based on the torque NIA cross B in the presence of the external magnetic field, and that the n hat vector wants to align itself. So for right now, we are just going to take it as a fact that the cues that are moving generate their own B field. Moving cues make B field. They're a source of B field. And we know that this coil wants to align, so what we are going to do is now look at this rotation of a north and a south in the presence of this external magnetic field, and we're going to put it in terms of the same structure that we did with the dipole rotation for the electric dipole. Now, our north and south we don't designate as positive or negative, because remember we said we don't have a beginning or an end point for magnetic fields. We have coming out of north and going into south. But to remind ourselves of what we did with the dipole rotation in the electric field, we introduced the P vector by definition as its own entity, as Q times D, because we saw that we could put the rotation, the torque, as P cross E, and the potential energy as negative P dot E, right? So if you go back and look at our electric field notes, so our potential energy was negative P dot E. The structure that we used was a dipole, defined a dipole moment, created it as its own entity, and reformulated the torque equation. Well, we're going to do the same thing. We're going to reformulate the torque equation by introducing, I'm going to talk more about this on the next page of notes, by introducing, by definition, a dipole moment vector. Now, instead of the P vector, we call it the Greek letter mu. So we're going to let NIA represent the dipole moment vector, just like we let P represent Q times D. It just becomes a convenient way of thinking about the rotations, just like it was for the electric fields. Now, this dipole moment vector actually can be thought of in an analogous way, a completely analogous way to QD, if we could isolate a north pole and a south pole and have one exist outside of the other, just like we can with positive and negative charge, right? You can take an electron and carry it away and have the electron do its electron thing, its charge, negative 1.6 times 10 to the minus 19 coulombs, all by itself. You don't have to have the proton with it. That is not true for magnets, or nature doesn't seem to indicate that that's true. We can't just cut off the north pole of the magnet and carry it away and the south pole disappears. When you break a magnet, if I take the north pole off, I've made another magnet. So we'll still have a south pole. So mathematically, we certainly could define this magnetic monopole strength, have like a charge strength for magnetism, but that does not seem to be presented in nature, and if you can find it, there's a Nobel Prize waiting for you. Okay, so let's see what introducing our magnetic dipole moment vector does for us relative to making it easier to visualize these rotations. So if we go back and think of the rotation of the coil in the magnetic field, and I'm certainly not going to go back through the derivations again, we just talked about that. So we have the torque is NIA, where A is the area vector, that green area vector. Curl your fingers in the direction of the current through the coil. Stick your right hand thumb out. That's the N hat. And we saw the N hat vector wants to align itself with the B field, the external B field, based on NIA N hat cross B, giving the torque. And what we are doing is letting the NIA N hat equal the dipole moment vector. So now the dipole moment vector, which has the same direction as our N hat vector, wants to align itself with the B field. So we now have mu cross B is the torque, and it's identical in concept in terms of thinking of the rotation of that dipole vector. So think of that dipole moment vector, whether it's an electric dipole moment vector or a magnetic dipole moment vector. Same idea, will rotate to align with the field. So we get mu cross B is the torque, like we had P cross E, mu cross B. And our energy equation is given by negative mu dot B. So let's think about that mu NIA N hat vector, that N hat rotation in the presence of the external field as a negative mu B cosine of theta value. Remember, potential energy is always about the change in potential energy, not a specific energy value. And just like we had with the dipole rotation in the electric field, we have a 0 joule value at the mid-energy range. So when we rotate this N hat vector back 180 degrees, or just a smidge under 180 degrees, we are at our maximum joule value, right? So we have the negative 180 and the negative up front are going to give us our positive, our maximum joule value, and I just chose 10 joules as an example here. So we're just working with numbers to make our discussion easier. At 0 degrees, cosine of 0 is positive 1, so we don't get 0 joules, but we get our most negative joule value, negative 10, which means our total energy available to us is 20 joules. We would start at 10 joules, drop down to 0 joules as it rotates, and then drop another 10 joules as we go to negative 10 joules. And we have to keep in mind and always be careful when talking about dipole rotations that the 0 potential energy does not mean no ability, no energy left to do anything. It's just a 0 joule value. And that is what we are going to use to calculate if we're going to that point or through that point. But it's always the delta U that gives us our meaning. And we'll have some homework problems to look at dipole rotations and talk more about this in class as well.